In this video, I'm going to go over the hydroboration-oxidation reaction and mechanism, where these are the reagents that represent the hydroboration-oxidation reaction, which is an anti-Markovnikov and syndication reaction, meaning that the alcohol will attach on the less substituted side, which is this carbon right here. And since this is syndication, it will be on the same side as the hydrogen on the other carbon, which forces this methyl to become a dash. The other product that we could get is this dash OH, making that dash H because it's in addition, forcing this methyl to become a wedge here. So here's the mechanism. Let's say we bring in the alkene. There are two parts. The first part is hydroboration, which is this first part right here. And now let's bring in our BH3. This BH3 only has 6 electrons, 2, 4, 6, meaning that it is missing 2 electrons and it has an empty pure orbital, which is an electrophile. The less subside is going to attack that boron because we want to form the more stable carbocation on the more subside. So when that happens, this boron here is going to have 4 bonds and a negative charge, which makes this a hydride donor because you could think of that as a H- ion, which is going to attack that positive carbocation at the same time. So we're going to do that at the same time, which is why this is a syn addition, because they're forced to attack on the same face. So let's just say that we make that into a wedged boron here with its 2 H's and a dash methyl, because we know that this is in addition, so the boron has to be on the same side as the hydrogen, which in this case, I chose it to be a wedge. So now we have BrH2. So then we could do this 2 times because we have 2 more hydrogens, right? Where we just bring in 2 more alkenes to do that same exact mechanism as this first part here, which would lead to this intermediate right here, Br3. And I would practice drawing those two reactions 2 times when you are first learning this reaction. Right. We have a methyl group there. And this is a methyl group where this is Br3, where we could make this simpler by signifying that that is the R group. So we could redraw that as B, 2 R's here. And I'm just going to draw out one of the R's here. Okay. Now, once we have our Br3, that's the end of the first step, hydroboration. Now we bring in the second step, oxidation, with the NaOH and hydrogen peroxide. So this is hydrogen peroxide here. We're going to bring in our NaOH, OH minus, to deprotonate this hydrogen peroxide and give us this conjugate base here, where that HOO minus is going to now attack the Br3 group that we made in the first step. Right? When that happens, we are going to get this intermediate right here. Where now this is going to be the weird step because this boron with 4 bonds, 1, 2, 3, 4, has a negative charge. So this is going to be the migration step here where I'm going to label that atom 1, 2, and 3 to keep track of everything. There's a bond between 2 and 3 now. That bond between 2 and 3 is going to migrate and make a bond between 1 and 3 and then kick out that OH group here as the leaving group. So when that happens, we're going to have this intermediate here, where the OH minus left as the leaving group. this O is still attached to the B, and that B is still attached to two R's, where this was atom 1, 2, and 3. There was a pink bond between atom 2 and 3 here, but I migrated that pink bond to make a bond between 1 and 3, which is now this bond right here, right? This boron here still has two R groups, which this OH minus can still attack its empty p orbital and do this whole process 2 times to give you BOR 3 times, right? Wait, I'm going to draw out one of those BORs here, right? Where this is the R group as this right here. These two things do the same exact mechanism as these over here, right? And instead of the OH minus attacking, it's actually going to be the OOH attacking that boron first, because we want this OH leaving group to leave after this migration step. So this is actually going to attack the boron 2 times, doing that migration step 2 times as well, giving us this BOR 3 times, right? Now, once we have done that, the hydroxide ion, HO minus, is going to attack that boron. And now we are going to have this boron with 4 bonds and a negative charge. Right? Where one of the OR groups is just going to leave. Where let's just kick out that OR group there, make that leave. That would give us this BOH, OR, OR, and now this O minus with its R group, right? Where this RO minus group can get protonated by a water molecule and give us our neutral alcohol, which we see that this is the anti-Markovnikov product, where that alcohol is on the anti-Markovnikov carbon, which is the exact same thing as this right here. And it's also syn addition because it is syn to that invisible hydrogen right there. So that's how we get to the anti-Markovnikov products here, where that's the main product, but this right here will keep reacting with OH minuses and kicking out ORs 2 times to get, let's say, boric acid, boron with 3 OHs, where since we're in basic conditions, all these acidic acids here are going to get deprotonated by NaOH to give us negative charge O minuses here, where the sodium ion Na plus will come around and stabilize and solvate those negative charges, which this whole thing here is Na3BO3 side product, where this here is the main product we are concerned about because that is the product that is anti-Markovnikov and syn addition, which is exactly this main product right here. So this was a long mechanism with a lot of repeat steps, and also including a weird migration step kicking out this bad leaving group OH. But I would just practice this mechanism over and over and over again until you could do it without looking at the notes, and hopefully it sticks on the exam if it does show up. But I do not think that this will show up at the exam, but we never know. And I hope that helps.